Okay, first example. A 1 kilogram mass hangs from a string. What is the tension in the string? So first I'm going to draw a picture of this problem. Let's say this is my ceiling. Here's my string. Maybe there's a hook on it. And then I have a little mass that's 1 kilogram hanging from that string. I want to know what is the tension in the string. So tension is what? Alright, so ultimately I'm trying to arrive at the tension in the string. Ft equals question mark. To do this, I need to figure out all the forces acting on the 1 kilogram mass. And then I need to realize something important about this situation. That is, that since the mass is hanging, that mass is stationary. It is not moving. And the word I gave you in the last video for that is static. So this block is in static equilibrium. And the things to remember about static equilibrium, all of the up forces equal the down forces. That is, the total force in y is 0. And all of the left forces equal the right forces. That is, all the forces in x come to 0. So in blue, color coding, because there's a lot going to be happening on this slide, let's draw the free body diagram so we can analyze all the forces. I start with the dot. That dot represents my 1 kilogram mass. And I know that 1 kilogram mass has on it a force of gravity. And since my mass is hanging from a string, there is a tension force resisting the force of gravity. Next, I know that since up forces equal down forces, Ft is clearly the up force, so Ft, and Fg is clearly the down force, the weight. Ft and Fg are equal in magnitude. I also know that my left forces equal my right forces, but if I go back to the diagram, there are no left and right forces to worry about. Okay, so now, using this simple equation I've set up right here, Ft equals Fg, I can find Ft. To do that, I will find Fg, which I can do easily because I have a mass. Fg equals mg. Fg equals 1 kilogram times, on Earth, g is about 10 newtons per kilogram. Therefore, Fg is about 10 newtons. And since Ft equals Fg, therefore, Ft is about 10 newtons. And if I really wanted to get picky and make these vectors, so I'll do that in a different color just so I don't confuse anybody. If I wanted to turn these into vectors, I'd have to assign a coordinate system. So let's call up positive, therefore down is negative. Gravity, which pulls down, would become negative. This force would be negative. And then Ft, as a vector, is pointing up, and so it would be positive. This question, though, is ultimately just asking for the amount, because there are only two directions, up and down. But if you were to say the vector Ft points up with 10 newtons, that would be fine. Alright, moving on to the next example. Alright, next problem. A 1 kilogram mass hangs from a string, and a 0.5 kilogram mass is hung on a string from the first string. What is the tension in each string? So just like before, this problem gets easy if I draw a diagram. So, first, I have my string, and I have my 1 kilogram mass. Then, I have another string, and a 0.5 kilogram mass. And the question asks me to find the tension in each string. So the tension here, and let's call that Ft1 for the first string, and the tension here. Let's call it Ft2 for the second string. These objects are both hanging, which is a key word to let us know they're not falling or moving upward, and therefore these objects are both static. Okay? Because of static equilibrium, I know a couple things. My up forces in each situation will equal my down forces. My left forces will equal my right forces in magnitude. Okay, so we're ultimately looking at the tension in each string. So let's make a free body diagram for everything in this situation. First, we have our 5 kilogram mass. And let's do these all in different colors. I'll do the 5 kilogram mass in orange. So our 5 kilogram mass has a weight, and then it has a tension from the string. Okay. Now we're actually going to do the string itself. So I'll do the string itself in purple. The string itself is experiencing that tension from the 5 kilogram mass. So there is a tension. The mass is pulling down on the string. And that's also balanced by the mass up above. Now that I've taken you through most of the hard stuff in the first two examples, this one should be pretty short. A 60 kilogram painter stands on a 20 kilogram scaffold. If the tension in one of the ropes is 500 newtons, what is the tension in the other rope? Now you might not know what this question means, so let's draw a picture. A scaffold is a thing you can stand on, supported by two ropes. So there's our scaffold, and I'll draw the ropes in purple. So here are our two ropes supporting the scaffold. They're holding it up above the air. So this guy's really high off the ground. So just to remind you, the ground would be somewhere down here. So our scaffold itself has a mass of 20 kilograms. So mass, and I'll use S for scaffold, MS is just the mass of the scaffold, is 20 kilograms. And our painter dude, MP, his mass is 60 kilograms. Okay. Fix my K up a little bit maybe. Or just make it worse. So I want to know what the tension in one of the ropes is. The problem says the tension in one rope, and we'll call it FT1, is 500 newtons. I'm now trying to find out what the tension in the other rope is. So FT2 equals question mark. Let's draw a free body diagram of this situation. We know that those ropes are holding up the painter and the scaffold. So I'm going to use a dot, and here my dot represents painter and scaffold is my dot. Alright, the painter and the scaffold together have gravity pulling down on them, so there's a force of gravity. And there are two ropes, each with a tension. And I'm going to draw these near the dot, just because it's hard to make them connect when you have more than one. But I have two tensions, FT1 and FT2. And because this thing is hanging, we know up forces equal down forces, and left forces equal right forces, but here there's nothing left and right, there's just up and down. Our down force is Fg, and we can go ahead and find that. Force of gravity equals mass times gravity. And I'm going to do both objects at one time, so I'm going to find the total force of gravity on the painter and the scaffold, so 60 kilograms and 20 kilograms, times force of gravity on Earth, 10 newtons per kilogram. 20 plus 60 is 80, times 10 is 800 newtons. Okay, that is my down force. My up forces are FT1 and FT2. That means that, different part of the problem, switching to a different color, all the up forces, FT1 plus FT2, have to equal Fg. which I just found out is 800 newtons. And Ft1, we already know from up here, is 500 newtons. So let's put that in. 500 newtons plus Ft2 equals 800 newtons. If I solve this for Ft2, move the 500 over, I get let me slow down. When I say move the 500 over, I do that by subtracting 500 from both sides, because here on the left it is added. So when I subtract 500 from both sides, I get Ft2 is 300 newtons, which is the answer to my question. What is the tension in the other rope? And I want to draw your attention back to, all I did to set this up is realize F up equals F down. That's the starting point for all static equilibrium problems. F up equals F down, F left equals F right. And that's how you start every single static equilibrium problem. And you can recognize static equilibrium problems when it gives you something like, what is the tension in one of the ropes? How much was the table pushing back up? Questions about forces. All right, one more example, then we're done. This is my next example, which I actually want you to think about. But my video, I'm realizing, is getting really long, and I think it could be helpful to do one example in front of you tomorrow and let you ask questions as I do it. So I will save this example for tomorrow. Why don't you go ahead and read it, think about it, maybe even try it. Notice that it doesn't say the known angle, it just says at a known angle. And so you would just call that theta, and then solve the problems in terms of theta. Try that, see what happens, and we'll take a look tomorrow.